Let's now examine block cipher modes. As you now know, you have to split a variable length plaintext into two fixed length blocks. The length is determined by the algorithm that you want to use. The way in which blocks are split is critical for the security of the entire ciphertext. We're moving into cryptographic systems now. Even a very secure algorithm, if it's ill-implemented, causes the ciphertext to be extremely vulnerable. We'll prove it in a moment. How can you transform data streams into fixed-length blocks? There are several common block cipher modes of operation. The first is rather euphemistically called the Electronic Codebook Mode, ECB. The second mode of operation is cipher block chaining, CBC. The third we'll cover is the counter mode, CTR. Finally, there are two similar modes of operation that we'll mention together. They are the so-called feedback modes, CFB and OFB. Let's start with the Electronic Codebook Mode. Assume you're a programmer. Your task is to split a long data block into pieces. You need to perform the same operation on each piece. What should you do in this case? Write a loop. Split the data into pieces, encrypt the first one and then another one, and so on. This is how the Electronic Codebook mode of operation works. The plaintext is split into blocks of the same length and each block is encrypted separately. First, this means that if the plaintext in two blocks repeats, you'll receive two ciphertexts that are the same. Each block will be encrypted into the same form. This is not a good solution. Secondly, this allows you to modify the ciphertext in a way that is transparent for the recipient. You can insert some blocks into the ciphertext, encrypt them, and thus change the content of the original message. The Electronic Codebook mode causes the security of the cipher to become non-existent. You should not use it under any circumstances. Other modes don't have these shortcomings. Let's take a look at the cipher block chaining mode. The point here is finding some relationship between individual blocks. As we've seen before, separate encryption is not the best idea. That's why cipher block chaining mode encryption involves XORing, combining the first block after encryption with the next block. The second block is also encrypted, XOR'd, and combined with the third block, and so on. This is a simple and elegant solution. There's one problem though. What to do with the first block? There's nothing to combine it with. We must use an initialization vector of some sort. What are the advantages of cipher block chaining mode? First of all, the initialization vector does not have to be encrypted. It's a pseudo-random string. There's no point in encrypting something that is already random to make it more random. Remember Kirchhoff's principle. The security of the ciphertext must depend solely on the security of the key. The second strength of this mode is that if you encrypt the same data using the same key, the output will be different. This is because the initialization vector is random. Also, if during transmission a message block becomes corrupted, it doesn't cause further damage. Obviously, you won't be able to decode the block, but this doesn't affect other blocks. If you combine the corrupted parts using the XOR operation, it will all be cancelled out. Other blocks will be readable and decryptable. The cipher block chaining mode is the default block cipher mode of operation utilized in nearly all Microsoft solutions. Let's now move on to the OFB and CFB feedback modes. The concept involved here is a bit different in that a simulation is performed that essentially changes a block cipher into a stream cipher. How can this be attempted? If you generate a key that has the same length as the plaintext, this would in fact create a stream cipher. Using the XOR operation, key bits are combined with plaintext bits. The implementation is as follows. Both modes contain shift registers. You've seen bit shifting before. The shifting in the two modes differs in that the operation is applied either at the start, before encrypting, or after encrypting. The bits will be shifted in one place or the other. This is the whole difference between CFB and OFB. At any rate, you'd need an initialization vector. It'll be the starting point to a cipher function. Remember that a key of an appropriate length has to be generated. Next, select the initialization vector bits and XOR them with plaintext bits. The output of this process is the first encrypted block. It is then shifted and the operation repeats. The last mode we'll mention is the counter mode, CTR. This mode of operation has gained wide popularity. One of the strengths it has is that you can decrypt a selected part of the ciphertext. You don't have to decrypt the whole of it. This idea is similar to the one applied in the previously mentioned modes. After selecting an initialization vector, encrypt it, thus making the key longer, and then combine it using the XOR operation with the plaintext.